Okay. Um, the floor is open, meaning feel free to, oh, there's another customer. Feel free to ask questions vocally or through chat. But I have to monitor the chat. All right. Let's go that way. All right. Who wants to go first? Just ask a question. Like it could be general, it could be specific. You can point me to a particular question on a quiz or a homework, whatever you want.
I have a question.
Go ahead, Masuma.
What will the test look like tomorrow?
Sure. So, oops, sorry, I clicked the wrong thing. So the test is going to basically look like this. There's going to be a question. You guys can see my screen, right?
Mm,
Where I'm writing? Okay. So the
no.
test.
Hi, Mr.
Hi,
Kretschmer.
Mr. Kretschmer.
Hi. Oh, how nice. It's the party house.
Yeah.
Okay.
He's so.
Don't take it personally. I'm muting you. Okay. So I'm going to describe what the test is about. Oops. Sorry. First, I'm going to keep clicking the waiting room. Okay. So on the test, the first page asks you about the following. It asks about precision.
Wait, are you writing on like a screen because we can't see it?
Oh, I forgot to screen share. Thank you. Let's screen share. That helps. Ta-da. Oops. How's that?
Perfect.
All right. Beautiful. Okay. Sorry, I just want to not neglect to let anyone in. Okay. Now I'm good. There they come. Yeah, so there's going to be a question about precision versus accuracy. So understand the basic difference between those as they apply to measurement, right? Precision is about consistency in measurement, meaning we get the same thing over and over. Accuracy is about the correctness of the measurement, meaning how close we are to getting the right value. And so I'm going to give you some kind of graphs of measurements that are taken over and over and ask you consistent versus uh, correct, meaning precision versus accuracy. So if you kind of just review the bullseye analogy, if you remember, we talked about that in one of the homework problems. That kind of idea, it's going to be a question based on that. Okay? So that's kind of like the first little chunk on the first page. The next page is going to have some questions on reading instruments and reporting them to the correct sig figs. So basically, questions similar to what was on the sig fig quiz. Okay? So that'll be that, and there could probably be some questions about how many sig figs in measurements. There could also be questions about rounding calculations based on sig figs. Okay? So that's going to be kind of the next primary chunk. Oops. Then the next chunk is going to have, I believe I have 5-dimensional analysis questions. And again, don't look at it and be like, ah, I'm done, I can't do it. You know, try to set it up with the units, and then you'll get at least partial credit for doing some of it right. So don't just be like, oh, I don't know how to do this from start to finish, I can't start. All right, work through it. And if that's what we need to practice the most today, that's what we'll do. Now, after that, and this is not the order necessarily because I'm gonna, like I said, I'm gonna cut the class, like half the people will go in the lab first, and half the people will just be writing first because I only have like 12 setups for the lab. Then there's gonna be just a lab portion, which is pretty short. It's just a question based on identifying substances using density. So this is going to require you to take some measurements with equipment that's provided on a couple objects to find their density. And based on what you find, to try to figure out from a table of given densities what substance is what. And that's basically it. So I think that pretty much covers the basic layout of the test. And again, that's why I told you, if you review and understand your quizzes, that's going to be a big piece, because that is what I've been doing is with those quizzes. I've been checking each skill as we go. So I would do that. I would say also the same thing, the labs. And then that should cover most of it. And then the homework, not that one really nasty set that we threw away, but the general problems with the homework. So there's really nothing to memorize. So you shouldn't focus your study by just looking and reading things. The best way to study for a performance test is to practice the performance. What I mean by that is you want to do practice problems primarily. You want to go through solving problems because that's what you're going to be asked to do, and that's how you study. So I hope, does that kind of satisfy the format of the test for you? Or do you have further question about that? And you can unmute if you have a question, but please just go back to mute, otherwise there's a lot of background noise.
So the lab portion is gonna be like the lab we did like yesterday, right? The
Yeah,
densities and
it'll
stuff.
have similar flavor, yes.
Okay.
But you won't have to do all the parts, you won't have to make graphs from it. You're just literally going to have to remember, right, what do I have to measure and how do I measure to find the density of this object? That's all.
For the lab portion, is it like just you or you and your lab partner?
Just you. I want each individual to do it. And that's why we're going to start with, like I said, I can put about 12 people into the lab at a time. I honestly don't think the lab portion should take more than 10 minutes if you know what you're doing, at least to take the measurements. And once you're done measuring, you don't have to stay there. You can go back to your seat, and then I can send someone else in. You know what I mean? But I'll definitely cut you off in the lab after about halfway. Otherwise, I'm not being fair to the other half. And then, again, don't forget, come during study hall. Come straight to our room so that you can do the test. And if you don't need the whole time, then whatever time you have left, you can quietly use as study hall anyway. And you won't have
So
any. Yeah, go ahead.
so why can't we just stay in your room, like, and then go to study hall and then come back?
Well, because you have our class, it depends what period I have you. If I have you like first period, that
Mhm.
works, right? Because
Yeah.
you come to class, and once you finish, if you finish, you go to study hall. Well, my other two classes have the study hall first, and so they don't know how much time they'll need necessarily, and so it's smarter for them to come to the for study hall first, and then you know what I mean. But that's why it's different for each class.
So, do we have to go check in with our study hall, or can we just stay in the classroom if we have it first period?
You can just stay, and I'm just going to take your IDs and I send them into the attendance office. I say, please excuse them from second period, and then you will be excused directly.
Okay, thank you.
Got you covered. Whatever I write on this document, by the way, it's being recorded on OBS, so I'll post that on YouTube when we're done, and then I'll also send out this document so you have a transcript of what we did. Okay,
Yeah,
go
can you
ahead.
go over what was it called? The significant figures?
Sure. You want me to do a general review of the rules?
Yeah, if you can, thanks.
I can. So again, I like to do it by justifying it, not just reminding you of what they are, but the more you understand why the rules are, the better you'll remember them. So sig fig rules really break down into two parts. One is reporting measurements, which really leads us to the counting rules. Like, how do we know when we look at a number written on a sheet of paper how many significant figures there are? Why does that matter? And how do we report a measurement on the paper to the correct number of digits to convey that information to someone who didn't make the measurements? And so we've seen this in a lab that we did. We tried to practice it a little bit in the density and the homework, whatever. So if we take the kind of, well, let me do it like this. I might as well just open, give me 1 second to open a file. I'll just open the first quiz we did just to kind of pluck the examples I want. And we go, sorry. There. Significant figures, original quiz. Here we go. Come on, open, you slowpoke. Thank you. Okay. So let me start from the pictures because I think that really justifies the rest. So when I'm looking at this graduated cylinder and I'm asked to report a measurement, first I have to find the correct position of the meniscus, which as we said is at the bottom of the smile right here. Okay. Then I have to look at carefully because some of you made this simple mistake. Some of you were literally just not reading the markings correctly, meaning you were like not looking at it as like the right increments. So this thick line is 50, so then it's 51, 52, 53, 54, 55, 56, etc. So when I look at where this is, first I'm going to report all the things I can read directly based on the markings. So we can all see that it's at least 52. I hate it when my thing does that. This thing gets wonky sometimes. But anyway, it's at least 52, right? Milliliters. But we can see it's past the 52, but less than 53. So you may say something like 52.1 or 2. I don't care what this digit is. The whole point is we don't know what it is. We just know that it's a little bit more than the line that we can see. The point is this has 3 significant figures. Now, so what, you might ask? Well, the point is also that if I was reading this number on a sheet of paper, okay, now let me kind of backwards engineer this. I would say, okay, somebody reported this measurement. How do I interpret this if I understand the rules? What they're telling me is the digit here is estimated. It's a guess between lines. What that also tells me is that the markings on the instrument went to the units place. And you can see when I look, that's exactly what this instrument looks like. It's marked to the nearest 1. That's the least increment. And then that last digit is the one that I have to estimate. But all of these are considered significant because they're part of how good the measurement is. Now let's say you thought it was right on the line and said, well, I'm going to call it 52. Good enough for me. Now look at why this matters. What you're now communicating is that this 2 is uncertain, that we only have 2 significant figures, and the fewer the significant figures in general, the less precise the measurement. But look at what this is implying. This is implying that our graduated cylinder was only marked every 10, that there were no markings in between, and that we saw something that looked like this and said, yeah, 52, but I'm not sure about the 2. This is critically important to see what this really means now. So if I wanted to report 52 on an instrument like this, I'd be telling you it's less certain because it's wavering in the ones place. So the percent difference is pretty big. But on this instrument, if I reported 52.0, what am I saying? I'm saying I think it lies between 51.9 and 52.1. I think it's somewhere in that range. Here I'm saying I think it's between 51 and 53. You see that's a big difference in range. And the wider the range, the more unsure I am. Let me pause here for a minute and see if that makes sense or if you have any questions about why I reported the way I did. Does anyone want to follow up on what I said so far? Oh, I see something in the chat. Let's hear.
So how do you know which numbers are significant and which aren't?
Right. So you see why this 2 is significant? We always keep the one estimate. And you notice this 0, if I thought it was 0, is also significant. And that's why when I write the rule zeros after the decimal point at the end of the number are always significant, that's where that comes from. Like understanding why those zeros matter. Because if I didn't include the 0 here and I just said 52, I'm telling you that the instrument I used is less precise. I'm telling you I measured it with something else than what I really did. And that's what significant means. Significant figures are telling me how precise the instrument is. So like if you look at this one's obviously harder to read. I can zoom in a little bit more. Oops. Or can I? Okay. But anywho, so again, if I'm using the same principle, on this ruler, I'm about here. I did it to me again. Oh my God. I think it's because I'm trying to write inside of a table and this writing thing doesn't like it, so I'm not going to write inside. So if you look here, I'm definitely at 6.7. It might be 6.8, but I'm not sure. But I know I'm at 6. I know I'm at least past the 7. But if I stop here, I'm not reporting enough significant figures because it looks like I can at least estimate that, oh, maybe it's 6.79, right?
So the last significant figure is basically your estimate of what you think it is.
Exactly. But the importance of reporting it is the fact that I'm telling you what the instrument looks like. I'm telling you this is marked to the nearest tenth of a centimeter. So I know that that's where the last mark is. So I'm telling you how good is your instrument. If I reported 6.8, then my instrument, I could backwards engineer it and I'd say, oh, this is marked to the 6 and then to the 7 and to the 8. I'm just going to do a snippet. And I think that my line ends somewhere here. And to say 6.8 is as good as I can say, right? I can't say any better. Does that make sense? Yes? Anyone? Thumbs up? Click a emoji or something? So the bottom line is that is why the reporting rules are what they are. And then just to look at this last example, 80, 1, 2, 3, 4, 5, 6, 7, but it looks like it falls somewhere between 87 and 88. Again, when I report it this way, I'm saying, here's my estimate. Oh, this was marked to the nearest 1. Now, if I reported it as 87.52, what would that imply about the thermometer I used? It would imply that I estimated the hundredths, which means I would have had a thermometer that was marked even finer, right, to finer lines. And so again, more significant figures in the measurement means a more precise instrument in general. So now let's go back and just discuss the counting rules, right? So if we go back to the counting rules now, when we count, here's what happens. It's really about the zeros, right? The non-zero digits that we report are always significant. So no matter what the digits are, if I'm reporting them, it implies that I measured or estimated. So that means 253.5 grams has 4 significant digits. There's just nothing to question there. 1, 2, 3, 4. And we assume this last digit reported is the estimated digit. The issue comes in with the zeros, right? It's the zeros that confuse us. So placeholders, I should say 0 placeholders, are not significant. That doesn't mean they're not important. It means they are not, so I can't talk and spell to say it. It means that they are not showing me anything about precision. They're not showing me anything about the measurement, except they're putting numbers into the right column to make the number the right size. So check this out. The way you recognize placeholders is when you're starting with zeros and you haven't hit a non-zero digit yet. So these are all placeholders until you hit a non-zero digit. Every single one of these, oops, I slipped. Go away. Every single one of these zeros are placeholders. Because if I take any of those zeros out, this slips into a new place value, and it's no longer the same size number. But that's the only purpose of these zeros. This only has one significant figure the way it's shown. The other place, which is a lot more ambiguous, and so we have to just decide and agree on a rule, is when we look at whole numbers like this. Again, without other information, we have to assume these are placeholders. And this also only has one significant figure. The problem, oh, go ahead. Yeah,
Sorry.
you good.
So when the 0 is like, so for the first one, it's like a bunch of zeros and then 1. Well, when the 0 comes after the 1, are those placeholders too? I mean,
No.
or
Let's prove that right now. Because I'm gonna just kind of do a little magic here. So right now, how would you read that number?
1,
How would you read that number?
10.
This 0 pushed the 1 forward into the tens place, right? Placeholder. How would you read that number?
1,
How would you read that number?
1.
Did this 0 push this over?
No.
That's not a placeholder. You see my point?
Okay. Yeah.
Therefore, since 1 equals 1 numerically, that point 0 must mean something else. And that's what I tried to show you when I measured the instruments, like I showed you reading the instruments. That is, when I put this 0 here, I'm saying, oh, I had an estimate at the tenths place, which means my markings were at least 1, but I thought it was on the line. If I wrote 1.50, now I'm saying 3 sig figs here. This had 2 sig figs. This only had 1 sig fig. But when I write this, I'm saying, oh, I could see that it was 1. I could see that it was around 1.5, but it looked like it was right on the line. It might have been 1.51. It might have been 1.49. But in general, this digit is a marking, and this last 0 is an estimate between lines. So the zeros,
So,
yeah, go ahead, Tom.
So if the 0 comes after any number, it's a significant figure.
Careful, that's not true here, right? The zeros came after a number. If a 0 is between digits, it's significant, right? This has 3. If it comes at the end, after the decimal, no matter how many I put, all of these at the end are significant. Because I don't need them to indicate the size. They're there to indicate precision. This has 6 significant figures. So the zeros, yeah.
So if there's like 8 zeros after a dot, there's at least 8. All those zeros are significant figures.
Assuming there was something before, right? Like here it wasn't. So the only thing you really have to keep straight is the placeholders. Once you just remember the placeholder zeros don't count, everything else does, right? It's just that simple. So if you really focus on this, yeah, go ahead.
So for the placeholders, it's just the ones that are like before the number, like after the decimal, and the ones that are after the number, like in front of the decimal.
Yeah, it's just until you hit a non-zero digit, don't count anything. And if it's a whole number with a bunch of zeros, they don't count because they're just assumed to be placeholders. Everything else counts. And then the other thing you have to remember about the counting rules is if it's a defined thing, or if we're counting like the number of something, like literally counting like how many things are in a basket, these are exact values. These are not subject to uncertainty in the way that measurements are. Measurements are limited because the instruments and our ability to read them have a limit, right? You can't read it to an infinite degree. There's a last marking and then an approximation. But when I define something, like when I say that 1 foot is 12 inches, that's not an approximation. That's an exact number, right? There's no uncertainty there. We said so. It's just we decided that. And if I count 20 eggs, that's not an uncertain thing. There's either 20 or there isn't. It's not like, it looks like it could be 21. No, either there is another one or there isn't. So those kind of things are exact and are not even subject to the concept of significant figures. Is that good, or do you want me to talk more about the counting part?
I have a question.
Yeah.
What does it say for defined, or what does it say?
Oh, I'm sorry. Yeah, that got smeared. Counting, when we just count things.
Okay.
Sorry, what happens is when I start writing too much on one document, it starts to get glitchy. I think, let me see, let me get rid of some stuff here. So I'll knock that one out. Okay, now that's the first part of the significant figures, the counting stuff, right? I'm gonna have to add more pages here. To be honest, I don't know how useful, oh, darn it. I don't know how useful this document's going to be to people who didn't see me make it because it's going to be so sloppy by the time I'm done. Yeah, I'll just start another page. Okay, so the second piece here is now the rounding calculations. Oy, why does that keep happening? That's bizarre. Every time I click. Okay, you stay then. Rounding calculations. So we've said that there's two different groups of rules. For addition and subtraction, it's the place value that we go by. For multiplication and division, it's the number of sig figs that guides us. So just to remind us, here it's the highest uncertain, highest in value, right? Highest meaning leftmost. Here it's just the fewest when we look at sig figs. So again, the justification for these rules comes from the basic ideas of where the uncertainty lies. So when we add numbers like 22.7 and 1.135, just as an example, we assume that the last reported significant digit is where the uncertainty is. We add the numbers just like math says we should, or if it's subtraction, subtract. So everyone would know to do this. But now we have to start asking ourselves, where is the highest uncertain place? And you can see if you take this two sets of numbers, it's here. This is where the uncertainty begins. And that's all we're allowed to keep. We're only allowed to keep up to the highest uncertain spot. But then we are allowed to use the next digit to round if necessary. In this case, the 3 doesn't round the 8, and we would report this as 23.8, with this tenths place being the uncertain value. That's all you have to know for doing addition or subtraction. Questions on that? Okay. Well, just to make the comparison crystal clear, let's do the same numbers, but let's multiply them. So instead of adding these two numbers, if I took 22.7 and multiplied it by 1.135, well, here's what my calculator says. If it'll wake up, here it comes. Hi, calculator. Where'd it go? So my calculator says 22.7 times 1.135 is all those ugly digits. And of course that happened. 25.7645. But this time, even though I'm using the exact same numbers, because I'm doing a multiplication, we're going to count the sig figs. This has 3. This one has 4. But I keep the fewest. So I'd have to cut off after the third digit, the third significant digit, and then round based on the number after. In this case, it rounds up. So I'm not looking at the place value this time. I'm looking at the number of significant figures. That's it. Those are the rules. Any questions?
I have a question.
Mhm.
Go over like the rounding thing. Where
Which,
like the question on the quiz was like round the following measurements to 3 significant.
oh, if I just tell you to, yeah, sure. So Some of the mistakes that we see there are with the zeros again, especially. So if I gave you, for example, uh, oops, people are popping in and out. If I gave you, for example, the number 26,395.219, and I say let's round this to 2 sig figs, right? So you have to start by going, from left to right, I have to start that way and pick 2 significant figures. So doesn't that cut off here? And the 3 doesn't round me, so I would just write a 2 and a 6. But then if you just say 2, 6, you can't represent 26,000 and change with the number 26. This is where the placeholders come in. You basically just have to knock out all the other numbers until you have the right size. So to 2 significant figures, this number is 26,000. That's it. And if we're going the other way,
Don't
oh, go ahead.
Don't-
Sorry.
don't you have to add the 3 like 0.000 for the 2 and 9?
If I do that, what happens? I now have 1, 2, 3, 4, 5, 6, 7, 8 significant digits. Right? Because all these zeros count after the decimal. And they make all the ones before count as well. Let me show you what that means, okay? So let's look at that, because I think it's important. That's where the mistakes keep happening. So when I say round this to 2 significant digits, I'm saying effectively that this is estimated. That it might have been 26,000, it might have been 27,000, it might have been 25,000. I'm really unsure. Now, this is a really weak measurement that way. But if I wrote what you said, I would be saying I think it's 26,000 to the nearest thousandth. It might be 26,000.001, or it might be 25,999.999. Do you see how narrow of an error that is? But that's why it has so many more significant digits if I report it that way. So no, you don't put those if you only want 2 significant figures. If I took the same exact number and said, well, let's round it to 3 significant figures instead. Well, now, if I start over, oops, we're going to go farther, right? We're going to go to the 3rd digit, and we're going to say, oh, 2, 6, and this rounds up to a 4. But what happens to the rest? I have to put the zeros here, so it's still around 26,000, right? When you round, your number should still be close to where you started. It can't be like thousands of times different. That's not rounding. That's like wrecking the number. So when you're rounding, the number value should be about what it was. What if I said let's round it to 4 significant figures? How would it look then? If I rounded it to 4 significant figures, then I go 1, 2, 3, 4. Now this we'd have a compounded round because the 9 rounds up, which forces the 3 to round up. So that's one of the weird ones because there's a 9. But this would go to 0 and this would go to 4. This would be 6 and 2. And then we just zero out this one and we'd be still around 26,000, right? Now the difference is here this would have significance. And that's where the ambiguity comes in. So if you wrote this, I'd be okay with it. But based on the rule I'm emphasizing, the better way to write this would be 2.640 times 10 to the 4th. Because now we're showing explicitly that this 0 is significant. Remember, the power of 10 doesn't have anything to do with anything but the size of the number. So the power of 10 is just like a way to show the placeholders again. But for the most part, you'd have to show that to be absolutely unambiguous, and so on and so forth. Now, if I took a number less than 1, like say 0.000059238, and said round that to 4 significant figures, you don't even start counting until you hit a non-zero digit, right? These are all placeholders. I haven't even started yet. Here's the first one. So 1, 2, 3, 4 would be here. That rounds up. I have to keep all these placeholders so the number's the right size. And then this rounds up to a 4. Done. Questions? Mazuma, that
So
was
if
you.
we
Yeah,
do
go ahead. Mhm.
if we do either on the test, you'd be fine with it.
Either what?
Like if we do the scientific notation
Oh,
or
yeah.
this way.
Either way, yeah, of course. They're both right. But I just wanted to double check with Masuma because this was your question. Did I satisfy you, or is there still questions on that?
I get it now.
Okay. Anyone else? Are we done with sig figs at this point, and you want to do the dimensional analysis?
Yeah.
Yeah.
Okay. Let's do
At
it.
one point, could you also go over the bullseye thing? 'Cause I
Oh,
wasn't-
yeah. Let's just put that up real quick. So what I'm saying there is the metaphor is if you have a dartboard, right? The goal is to hit the center. So kind of like with measurement, accuracy means you're hitting the target. So I better keep the bullseye lighter so I can draw on it. Sorry. So like if you start taking shots at the dartboard and this is where you're hitting, right? You're very consistently hitting the target. This is precise because of your consistency, and it's accurate because you're hitting the target. You're getting the right answer. But if instead your shots look like this, you're being very consistent, but you're not accurate because you're not hitting the target. On the other hand, you can be all over the board and never really hitting the target. Now you're not precise because you're all over the board, and you're not accurate because you're not hitting the target. And then the weirder case might be something like this, where you're kind of all around the target. So you're starting to get pretty accurate because you're close to the target. I'll say accurate-ish. But you're not really precise because you're still dancing all around. But this can be fixed by taking an average, right? You have a very accurate average. And so I tried to make a point that when you have a situation like this, where you're dancing around the answer, this is what's known as random error. It's fluctuations in the instrument. It's just making random errors in reading the instrument, whatever. And that's why taking lots of measurements will average us out to where it should be. That's why we take lots of trials when we're doing good measurements. But when you have high precision and low accuracy, that's usually referred to as a systematic error. That means there's something that's consistently off. Like your balance isn't calibrated, so it always gives the same wrong measurement. It's giving good measurements in the sense that it's always doing the same, but because it's not calibrated right, it's giving you the wrong answers. And to fix that, we have to fix the process or the instrument. So if I calibrate the balance, I'll move the answers to the right place. And so that's why knowing what kind of error you're looking at, whether it's precision problem or an accuracy problem, that's going to tell you how to deal with it and how to improve your measurement and your experiment. So that was the essence of the dartboard thing. Was that good enough to clarify it, or? Not sure who asked.
Then.
Yeah, thank you.
Oh, sure. Yeah, question.
So how would this look like on a different test, a different example? Like, what would the question be? Like,
Sure.
what would you?
So consider this, and I'm not going to give too much specifics here, but instead of a dartboard, there's other ways I can represent data, right? So I think a really easy one that would be, I should say easy to interpret, would be like a histogram. So I'm sure you've seen histograms even if you don't remember the name, but something like this. Imagine a graph that looks like this, where you have a bunch of measurements. And so, you have ranges of possible values. So let's say it was like 2, 4, 6, 8. And on here you have like how many of each there are, right? And then you stack them into like bars, like kind of like a bar graph. Well, let's do it in 2 different colors on the same set. Let's say in the one case, almost all the measurements are stacking up here, and then there's a little variation around the edges, right? But let's say in another case, your measurements are stacking up all over the place, right? Which group of measurements shows higher precision, the blue or the red?
The blue,
Why?
because they're like closer together and
Yeah,
like
that's it,
more compact.
right? It's just another way of like this, like thinking of the dartboard thing. What this is showing is the number of measurements that are the same are very huge, right? Most of your measurements are around the same when the blue data are shown. But the red is showing values all over the place. And so it's very inconsistent. So that's another way you could represent something like that, right? And there's other ways too, but I just wanted to give you at least one other example. Did that make sense as an example, or?
Yeah.
Yeah. Also, so sorry.
It's good.
So when the bar, so like one of these graphs, so if the thing is like going higher, but it's going higher at like the same rate, so it's like it's at the first line, and then at the second one it's at the second line, and then
Mhm.
like that'd be consistency, or would that be?
It depends what we're measuring. So I would say if we were trying to, for example, measure the length of a table over and over again, what should it be, right? What should the histogram look like? Ideally, if the table was 6 feet long, 100% of the measurements would be here, right? You can't get any better than all the measurements being exactly the same. That would be consistency. But you're more likely, depending on the instrument you use, to get a spread, right? So here I'll just draw a smooth instead of as a histogram. So with this spread, the width of the spread determines how consistent you are. This is more consistent, for example, than this. Oh my gosh, that I hit the button. Sorry about that. I hit a button on my pen and it went cuckoo. Cuckoo for Cocoa Puffs. Mary, I saw that you asked about the notes being posted. What I'm going to do is I'm going to upload this video and I'll just send the video because I don't know how much sense the notes are going to make on their own because I'm scribbling all over the place. But you can watch the video again if you want to, see any part of it more slowly later. But what I was trying to say was, even if we're centered around the same value, so if you look at it like this, right? Both of these on average say 6, don't they? They both are peaking at 6, and on average it's about 6. So they're both giving the same average value, but the red is much wider. So it's showing a bigger spread of values and therefore less precision. So hope that answered that. All right, so let's look at some dimensional analysis because this is the place where I think we were the weakest. And I found a really nice thing earlier. Let me see if I can find it again. Where was it? I should have just downloaded it because it was actually really nice. Do I have it here? Hold on a second, folks. I bet you if I search it up, I get it'll come up. Hold on, I will find it, and then I will show it to you, and if you want, I will send it to you as well. But it's got all the problems already worked out. And what I liked about it was it kind of increases in level. So here's what it looks like. Okay, so it gives you a bank of conversions, and then it starts with relatively simple problems, and it works its way up to harder problems. So there's like 6 pages of these, right? Check it out. But what I would do if I send this to you, you can either like start with it, scroll down so you can't see the answer right away, or print it and then like cover the answer, and then try to set it up and solve it and just work your way through it. Oops. So you'll see these are pretty simple ones. They're like single part. They get harder, and then there's more parts coming, right? And it's kind of in a word problem format and like that.
Are you gonna give us the conversation factors on the test?
The
Do we have
conversions,
to
yeah.
the
And if I miss
conversion?
any, if you think I forgot something, just ask me during the test and I'll say, oh, and I'll throw it on the board, okay?
Okay.
I do not intend or want you to memorize stuff. I want you to learn. And here, these are better because these are the word problem. Like some of these are annoyingly long. But again, if you can do these, you're going to be golden. Let me give you one that I think is interesting because it not only is cool from the point of view of solving a problem with dimensional analysis, but it actually says something very interesting about the world. Check it out. So it turns out that the sun, meaning our star that we have in the sky, is about 93 million miles from Earth. Okay? My question is, how many minutes does it take light from the sun to reach us if light travels at, and let's make this a little harder, 3 times 10 to the 8th meters per second. Now, if I gave you a problem like that, here's what I would also tell you. I would tell you, for example, that 1 mile is worth about 1,609 meters. So you'd have that conversion. Now, I don't think I should need to tell you anything else because you should understand time conversions between minutes and seconds, right? But when you look at this problem, and any dimensional analysis problem in general, I think what's really important to do is to kind of highlight the information so you understand what you're dealing with. Start with, well, how do I know where I start? Do I start with this number? Do I start with this number? And here's my general rule of thumb. When you see a unit over a unit, that's usually a converter. In other words, that's a relationship that's going to be used to change from one unit to another. So usually, the thing I'm starting with will have 1 unit, like this, and the thing I'm ending with will be 1 unit, like this, almost always. The only time that's not true is if we convert a ratio, like meters per second and kilometers per hour. But what I'm saying is, you start from a unit, and then the other things are relationships between them. So in this case, it seems we should start at 93 million miles. And it seems we want to end at minutes. So at the end of the string, we're aiming for minutes. So we have to somehow connect from here to here with what's given. So now let's start planning how that's going to look. Well, I don't have a direct link, so it's going to take more than one step. So let me start by lining up things. Well, I know I don't want to end in miles. That has to go away. And I know I can't get to minutes right away. But is there a connection between them that you see? Like, is there some way to connect those dots? Like, where could I go next if I was going to eliminate?
You could use meters.
Good. Because if I take the miles and change it into meters, then I'll have a connection from the meter to the second, which is time, right? Which is where I want to end up. So at this point, since I've been told that each mile is worth this many meters, that puts me at this position. But I don't want to end here. I want to eventually get to minutes. But wait a second. I don't have a connection between meters and minutes. And yet I know I don't want the meters to stay. Is there some way to connect the meters to time, if not minutes?
Seconds.
Yeah, because this speed is literally telling me how many meters, and of course I didn't give myself enough room. Whoops. Each second, right? And now hopefully it's obvious that at this point to get to minutes I just have to use a common conversion that I already know, because each minute is worth 60 seconds. Now, if you can't see that as soon as you read the problem, neither panic nor give up. Just start somewhere. Pick something that has just a one given unit and aim for the thing that has one given unit at the other side, and then look for the pieces that connect them like a string. And then mathematically, let's calculate this because like I said, there's a very interesting result. If you take 93 million, multiply by 1609, divide by 3 times 10 to the 8, and then divide by 60, the answer comes out to about 8.3. I'm only using 2 sig figs. Now think about what that means in real practical purposes. It means that we cannot detect anything happening from the sun for at least 8 minutes. If the sun blew up right now, there's no way to know it for 8 minutes. Even if we were standing right there and trying to call Earth, radio signals travel at the speed of light. The speed of light is the fastest speed of anything. Nothing made of matter can travel as fast, nor faster as far as we know. And what that really means is that as you look deeper into space, you look further back in time. If there's an intelligent race on a planet far away from us, let's say, I don't know, a few 100 million years away from us, 100 light years, a few 100 million light years, as they point their telescopes at Earth, they're seeing right now light that left hundreds of millions of years ago. They might be seeing dinosaurs walking around on Earth. I mean, you'd have to have a really powerful telescope. But my point is, we think of light as instant, like you flip a switch and the light's everywhere. But it's not. It's just super fast. So under the scale of distance that we live, it seems instantaneous. But even for a light beam to travel around the Earth takes at least half a second. So the farther you look back in the space, the farther you look back into time. And that's where cosmology tries to figure out, well, how did the universe start? If we look in the deepest reaches of space that we can detect, we see close to the beginning of the universe unfolding. It's kind of interesting when you think of it that way. But anyway, questions about the process is what's important here.
Could you go over the dimensional analysis quiz we took?
Sure. The first one?
Yeah.
Let me open that up. Voila. Okay. So I'm going to try to use the strategy I just outlined in terms of where to start, where to finish, and let's put in this one, I think interesting, the metric prefixes were troubling us a lot. So I'm going to show you what I think is a slicker way, maybe an easier way to apply them. So given that I told you that milli was worth 10 to the minus third, and that kilo was worth 10 to the positive third, let me kind of also pull out of the problem what else I know. This is saying each aspirin must have this mass. So to me, that's a relationship. That's telling me that one aspirin equals this many milligrams. Okay? Now check it out. I can see that I have to start here because, again, this only has 1 unit. And I'm asking for how many aspirin, which is 1 unit. So my goal is to start with this 25 kilograms and come up with a sequence of connections that ends up counting the number of aspirin that I can make. So this is the final answer, right? Now, I don't have a direct connection because nowhere in the problem does it say, oh, this many kilograms for 1 aspirin. So we're going to have to string some pieces together. Now, hopefully you can see, since the aspirin are connected to the milligrams, that I'm going to have to take this kilogram and break it down to milligram. And I think some of you are having trouble doing it in one step. Here's my advice. Get rid of the kilogram, but instead of going straight to milligram, just go to the base unit. In other words, go to the unit that without the prefix. Because then you only have to play with one prefix at a time. And you might find this easier. So let's start there and see what happens. Now we need the relationship, and all I told you is that kilo means 1,000. So think about that. The top and the bottom of this fraction have to be equal amounts. The bottom right now already has the kilo next to the gram. To make it fair, to make it equal, I have to put an equal amount next to this gram. Well, I'm not just going to put another K. That would work, but it doesn't really solve anything for me. I'm going to put what it's worth. How much is kilo worth? It's worth what's worth my eraser not working? Okay, go ahead. Crap out on me. I dare you, computer. Now this is where it's going to say, oh, your computer is still cuckoo. Hold on, I'm going to have to restart Word. No, I was so close. Sorry. I was just about to get to the good part, too. Oy. Okay, I'm not going to wait. Just close it. Leave me alone, stupid computer. Thank you. And we come back. Well, we're back, ladies and gentlemen. Thank you very much. Okay, this happens about once every half hour or so. Okie dokie, let's bring this one back. It's the only one I need right now. Wah, it's gone. All right, well, where were we? We were at 25 kilograms. We were about to do this, and we were already telling you that kilo meant this, and milli meant this, and that each aspirin is worth 250 milligrams. So what I was trying to say was that instead of converting it straight to kilograms, let's go to grams. I was telling you that since kilo means 1,000, and the top and the bottom have to be equal, well then 1 kilogram is worth 1,000 grams. This is the only information you need to know to figure that out. Because if I put kilo in front of anything, I'm making that unit 1,000 times bigger. If this unit is bigger, I need more of the small units to equal the one big one. This is critical now. If you have any questions about why I'm putting this number here, you have to ask. And I don't have to write it that way. I could have also written it directly as the scientific notation equivalent. But it's really the same, right? Let me pause here in case you have a question on that.
Wait, so grams? So you're saying 1 kg would have 1,000 grams?
That's right.
And you got that because it says 1 kilo is equal to 10 to the third
Right.
power?
Right. So if I did this, a kilo ishal, that would mean I've created you. It took 1,000 of you and glued it into one giant person. So a kilo ishal would be 1,000 of you, all stuck together as one giant piece. So a kilogram is like taking a bunch of little grams and gluing them together. Obviously, not just a bunch, but I'm not going to draw 1,000 of these, okay? But it's like now it became one big thing, right?
Mm-hmm.
And so it takes 1,000 of those little pieces to build that one big thing. That's what this is saying.
Okay.
Does that make sense?
Yeah.
Okay. Now at this point we can't stop because we're only at grams. We got to scale back the other way, meaning now that we're at grams, we can head toward the milligrams since that's going to get us finally to aspirin. But what happens now? Well, again, we have a choice here. We can think in terms of fractions or we can think in terms of scientific notation or decimals, but here's the bottom line. In this case, you'll notice the letter, the prefix is on this side. So I've already given this gram something. This gram needs an equal amount. But what does milli equal? It equals 10 to the negative third. So what I'm saying here is that when I take milli and put it in front of something, I'm just taking 1,000th of it. In other words, I'm cutting it into 1,000 pieces and taking just one little piece. So what this is saying is that 1 milligram, and I'll write it up here, is literally 1,000th of the original gram. You can write it this way, But you should also understand that it's the same thing as writing it this way. What? How could that be possible?
So you could put it both ways?
Yeah, but notice I changed the sign, right? It was 10 to the minus
Oh.
third down here, but it's 10 to the positive third up here.
Oh, okay.
But why? Why does that work? On the top side, what I'm saying is if I take 1,000 of the little pieces, I'll rebuild the gram. On the bottom side, I'm saying if I just take one little piece, it's worth only this fraction of a gram. Right? It's saying the same thing two different ways. I'll give you another example. Isn't there 100 pennies in a dollar? Does everybody agree with that? 100 pennies is $1. Yes? In other words, let me write this kind of in the notation. There's 10 to the second pennies per dollar. But couldn't you also say that 1 penny is 100th of a dollar? Aren't these saying the same thing a little different way? That's what I'm getting at. So either way you write it. Now, the reason I wrote it this way is because when you look at it this way, I'm literally just taking the value of the prefix and putting it next to the base unit. Just like I took the letter of the prefix and put it next to the base unit. And that way it's really visually easy to put the numbers in the right place. And now the math. Now technically you shouldn't need a calculator because these are just powers of 10, but let's put it in the calculator anyway for the practice of using the powers of 10 on the calculator. So, I still have one more thing to do. Sorry, I'm not ready to calculate yet because I'm almost done, except I'm not asking how many milligrams do I have, I'm asking how many aspirin. And since I have a connection between those things, I can now do this, and I see that each aspirin requires 250 milligrams. Now I can go to the calculator. So it's 25 times, and if you want to put 10 to the third in your calculator, whoops, the best way to do it is with that double E button. So I would do 1 times 10 to the third. That's how you can enter. You notice I didn't type 10. The 10 is built into the E. When you see E on these calculators, it means times 10 to the power that comes after. So this is me multiplying 25 times 10 to the third. I want to divide by 10 to the negative third. And then I'm going to divide that by 250. And when I'm done, I get 100,000, which was the answer. Now, when I grade this part of the test, I'm not just going to look at the answer. I want to see the layout, and especially I want to see how the units are put in place and canceling. That's what dimensional analysis is. If you're not showing all of that, you're not actually doing the problem. That's what I'm looking at, because it's that logical alignment that teaches us how to solve the problem. Question?
So on the test,
Are you still talking? Because I can't hear you. Safi, I'm not hearing. I'm not sure what you said.
can you hear me?
Now I can, yeah.
Okay. Okay. I don't know why I wasn't working. Anyways, so on the test, are you gonna put like these type of? Are they gonna be like really big, or are they gonna be like this?
What do you mean by really big?
Like, are they gonna have like a bunch of different like units?
Oh, I see. Oops. They're not going to be. They're not going to be crazy, but like even that one I did with the speed of light a second ago, right? Like, I think that's fair game. It's got like 3 or 4 steps, but I'm not going to have you do like a 20-step problem, no. But this, to me, was, a reasonably medium problem. Like an easy problem would be like a single step, right? It's just, oh, this changes to that, done. But that's not really testing you much. So I'll probably put things like in the medium zone. And I'm going to purposely pick units you've never heard of because I actually want to force you to have to solve it by lining up the units. Now, continuing on this quest, the mass of a lead cube that has this length and this density. Now that we learned density, we could use an equation, but this was before we learned it. So because it's a cube, I expected you to think of it this way. That it has a side of 20 centimeters, okay? And some of you just took that and used it as if it were the volume, but it's not. Because if I know the length of a cube, since it's a cube, I also know the width and I also know the height. And I believe I had told you on this information that a milliliter is the same as a cubic centimeter, so that it would inspire you to go, oh, well, if the cube has these dimensions and I multiply them all out, I'll find its volume in cubic centimeters, which is the same thing as saying if I took the 20 centimeters and cubed it, that I believe comes out to 8,000 cubic centimeters. So if I start there, and I want to ultimately get the mass, which is the grams, I just have to connect the dots. So I can see that my grams is connected to milliliters, but my milliliters is connected to cubic centimeters. And so I can work backwards by doing this, just to be explicit about the fact that these are the same. And then based on the way this density is presented and the way the units have to work out, I can see that I need to put it this way, which is to say 11.3 grams per every 1 milliliter. And it tells me to just multiply these two numbers. I think it was 90,040 or something like, or 400. Or was it 90? I think that was right. I'll double check it. So 11.3 times 8,000. Yeah, that's what it was. So I think what's causing confusion, and I get why, is when you see this and this, it looks like there's absolutely no connection between the two. They look completely alien to each other. But that's because I'm used to this, and you're not. And so that's why I told you when I first introduced this, you should, remember this, because I knew it was going to keep coming up since we do a lot of volume measurements in chemistry. And hopefully you're starting to get a little better at that recognition because we used it also in the density lab, etc.
So where'd you get the 8,000 from?
Well, I found the volume of this cube. I did 20 times 20 times 20, which is 20 cubed.
Oh.
Yeah.
So do you need like the middle one where it's 1 ml over 1 centimeters cubed?
Explicitly, you really wouldn't have needed to write that. You could have said, I already know that it's the same, so I just start from 8,000 milliliters and do the last step. But you'd have to know that. In other words, if you didn't know this, you might be like looking at it like, well, they're not connected. So no, you don't really need to do this. This is literally kind of a useless conversion. It's just being explicit about the units being equal, right? But yeah, I don't think you need that. Now this last one kind of harkens back to the first one in terms of using metric prefixes. Meaning, if we start from nanoseconds, and instead of going straight to milliseconds, first turn it into seconds, then turn it into milliseconds, it looks a lot easier because as long as you know that nano is 10 to the minus 9 and that milli is 10 to the minus 3, then you can just do this. Oh, nano is that? So if there's nano down here, there has to be nano worth up here, right? Now the top and the bottom say the same thing in a different way. 1 tiny billionth of a second is a billionth of a second. And same here. Since there's milli on top, I need the equivalent of milli on the bottom, like that. 1 millisecond is the same as this many seconds. See, I really want to emphasize visually that I'm making the top and bottom equal. This equals this, right? And seconds equals seconds. So the top and the bottom have equivalent amounts of stuff. Milli equals this, top and bottom are the same. Seconds equals seconds, top and bottom are the same. And that's why I'm putting it the way I do. And that's why I'm also telling you for metric conversions with prefixes, it might be easier to go to the base unit first, then convert it to the new prefix. And again, because these are powers of 10, if you remember the rules of powers of 10, it's really easy to solve because when you multiply 10 to the 12th by 10 to the negative 9, you just add the exponents. So this just becomes 10 to the third. And when you divide powers of 10, you subtract the exponents. So it would be 3 minus negative 3, which is 6. So that means it all just boils down to 9.86 times 10 to the 6th. No calculator was involved. And that was that quiz. So was that okay, or was there still stuff you wanted me to talk about it?
What if instead of putting it in a scientific notation, you put it into like a whole number?
Sure. Well, it would be kind of annoying because here you'd have to write 0.000000, or you'd have to write 1 over 1,000,000,000,000, and then here you'd have to write 1 over 000, or 1 over 1,000,000. You can do it, but especially when they get extraordinarily large or small, it's just getting annoying to write it out. Do you know what I mean? And the other thing I would point out, and I was making this point to another group I was helping, if you're doing that, if that's your instinct, it tells me that you're just uncomfortable with powers of 10. And that means you have already been uncomfortable with powers of 10 for a long time. And sorry, I think you cut out when I was explaining. So basically what I was trying to say was, if you're trying to avoid using powers of 10, it's like you're saying, well, kind of, I don't like how that looks. I don't get it. I'm just going to avoid it. But the fact is that the first time you saw it, you did the same thing, and maybe you don't remember. And all the time that you've probably seen it again, you kind of just dodged it and kept getting around it. And that's why you never learned it. Otherwise, it would just be easy to you, like it is to me. It doesn't make me smart. It just, I know it. And once you know it, you got it. So my challenge to you is, when things are uncomfortable, don't dodge and try to avoid them until they go by, because then you're just going to encounter it again and trip over it. Work through it. Just take a stand. Say, you know what? This is the time I'm going to actually sit with this and work to really understand it. And once you get it, once it clicks, it doesn't go away. Think about things in life that are complicated, that once they're there, they don't go away. Riding a bike, tying your shoes, things like that. You know, you struggled first. And if you kept saying, nah, maybe I'll try it, I'm not gonna, you'd never learn. Again, I know it's not a big deal. It's powers of 10. But it really does make the math easier. This is the whole point why they did the metric system. Because before there were calculators, it was easier to do math. Anyway, enough of the soapboxing. What else can I do for y'all?
So on the test, so if you take it and like you don't get a grade you like, can you retake it or no?
So the first level is the correction. So I would say it depends, because I don't think you have to necessarily take a whole test over. Like, there are specific skills on each test, right? So let's say you do great on this part, you do great on that part, and you really bomb the, dimensional analysis. And what I would think is, well, let me write you a new dimensional analysis portion, let you retake that part, and then just combine it into your original score. You know what I mean? Like, just fix that part. So that's kind of how I'm thinking about it. Let's focus on the skill that troubles you, and then fix it at that level. Does that make sense? Or? But let's not plan for failure. Let's plan for success, and then, and again, I don't think of it as failure. To me, failure is just learning how not to do something. And then from that point, success is figuring out how to do it. So you never fail if you don't stop trying. You only fail when you give up.
How many points is the test?
I'm not sure if I added them up yet. It'll be probably similar to, part one. That was in the like 30 something points.
Okay.
But
And it's
tests,
just
yeah,
like all written, right?
right. There's no multiple choice on this.
Okay.
And the good news is that I'm preparing you because our final exam this year we're writing to be a performance-based test. So there'll be some written questions and there'll be some lab parts. So to prepare you, I'm trying to test you that way throughout the year. So when you get there, it's not like a big shock. All of a sudden we're doing a lab for a test. I mean, so far that's mostly what we've been doing. So
Do you have like a website or worksheet we could have that would help us like practice this stuff for tomorrow?
which specific stuff?
Oh, what we were just going over.
Yeah, so this is the one I just found that has like lots of problems and they're already solved. So you can like not look at the solution, like kind of cover the solution and then work through it and then you'll have the answer key in front of you.
Can you email that to all of us?
Do it right now.
Thank you.
Mhm.
Thank you.
Of course.
Thank you.
And all I did was Google dimensional analysis word problems. So that's something you could also do, right? I mean, you could literally find more if you wanted to. I made an honors chemistry group. Yay. Dim and analysis practice. Voila. It should be coming to you as we speak. At least the link should. The rest is up to you.
Can you go back to the quiz that you just had open?
Sure.
How did you get 3 minus -3? Like I don't know where you see that.
Sure. So when I combine the 10 to the 12 and the 10 to the minus 9, I added those exponents, and it gave me 10 to the third, right? And then now I have in the numerator 10 to the third, and the denominator is 10 to the negative third. So when you divide powers of 10, you subtract their exponents. And that's why I'm taking this 3 and this -3, and I'm subtracting them.
Oh yeah, I forgot about that.
Does that make sense?
Yeah.
Now here's part of the reason you may not remember some of the things you learned in the past, and not just you, I'm talking to everybody. It was probably never explained to you why you're doing it and why it works. And that's why I always try to explain why things work, not just what it is. So let's look at that rule and see why does that happen. I mean, it's really simple logic once you see it. Isn't 10 squared just 10 times 10? Yes. Isn't 10 cubed just 10 times 10 times 10? So if you multiply 10 squared by 10 to the third, aren't you just doing 10 times 10 times 10 times 10 times 10? Sorry, I'm starting to get monotonous. Well, how many 10s did I just put? 5. 3 plus 2 is 5. That's why the exponents add, because you're literally just counting up how many 10s you're putting together. That's the basis of that rule. It's not just something somebody came up with, like, oh, let's just add exponents and see what happens. It comes from math. And when you divide exponents, it's just going the other way. If I take 10 to the third and divide it by 10 to the second, I'm taking 10 times 10 times 10 and dividing it by 10 times 10. Well, all but one of the 10s cancels, and so 3 minus 2 is 1. That's all you're doing. That's why that's the rule. Now, the other weird thing is, what does it mean to say 10 to the minus 3? Well, we know it moves the decimal, but why? Because what this is really saying is you're dividing by that many powers of 10. That's what the negative exponent really means here. You're taking 1 over 10 to the third, and you're multiplying by that, which is like dividing by that many powers of 10. That's why the decimal moves the way it does. When you multiply by powers of 10, you're moving the decimal to the right. When you're dividing by powers of 10, you're moving the decimal to the left. Right? All of these little tricks and rules that somebody made you memorize when you were in grade school, had a reason. And if you never understood the reason, well, then you're just going to forget it all, right? It's just going to kind of fall away, unless you just happen to have a good memory. But memory is helped by understanding. Just raw memorization, it doesn't have anywhere to stick to. Anyway, just a little aside there. Any other questions that I can help you with that you think will prepare you?
Can you go back to that dimensional analysis sheet, the when you're talking about with like the 6 pages or something?
Oh, sure. Here it is. Yeah.
So you know how you said they get progressively harder?
Sure.
How much harder down that sheet would you say we'd be seeing tomorrow?
So something in the neighborhood of the problems that have like 3 to 4 steps is as hard as it'll be. Like, again, cubic meters, I'm not going to do that to you because that's an annoying thing. Although here it wasn't as bad because they gave you a direct conversion. So I think it's here somewhere. Yeah, they tell you what a cubic meter is, right? So I'm not going to make you do a bunch of just convoluted things that are impractical. But just to give you a sense of difficulty, I would say a problem has 3 to 5 steps is the worst I would give you. Like,
Okay, thank you.
yeah, I think that's good.
Okay.
Yeah, I'm not going to give you on this test something that requires that. So, anyway, some of them are fun to do. That's why those challenge problems that I had on my website, the hamburger problems, some of those are fun to try just because they're silly or it's kind of interesting. But whatever. What else is there we can talk about at this point? Because me talking isn't going to do much at this point. My talk is to clarify so you can practice properly. But if you think that me just having said it to you and you watching me and you saying, oh yeah, that makes sense, is going to make you a better problem solver, it's not. The only thing I can do is show you how. The only way you can improve is to practice it the right way. If I could just say it and you knew it, either I would be a genius or your brain would just be so receptively easy to program, it would take no practice. But there aren't many people like that in the world. So you have to practice. That's why I give you homework. That's why I give you stuff to work on. It's not to punish you. It's not to drive you crazy. And it's not to take up your free time. It's to make you better at what I'm asking you to learn. All right. The questions seem to be slowing. So maybe we should call it, give you guys some chance to practice. And then I'll be in school in the morning by 7 in the room if you want to come in for last minute questions. And I'll post this video as soon as we're done, and I'll send you the link to it in case you want to watch any parts of it over. Sound good?
Yep.
Okay. Then we shall, yeah, my voice will be in the video. I'm just seeing the questions. Yeah, if I'm gonna, I'll kind of hang out for a few more minutes if anyone wants to stick around. But other than that, I'll say like 9:30 for sure. I'm done. So otherwise, have a good night. Don't overdo it. Get some sleep, and just do your best.
Thank you, Mr. Kretzos.
Thank you.
All
Thanks
right,
for
thank you
thanks for
so
Thank
joining
you.
us.
Have a nice night.
All right, we'll see you in the morning.
Bye.
Bye bye.
Thank you.
Okay.
Bye.
Thank you.
Bye. Take care. All right, Masumi, you said you had a question or so?
Yeah. Okay. So for the chem lab today, right?
Hmm?
After the graph thing that we did, the question was, what does the graph show you about the density of the substance? I said that the graph shows that the density remains consistent throughout, right?
Hmm?
But then it asks, does it depend on how much substance you measure? I kind of got confused on that.
So let's put it this way. When you look at the plot, let me just fix this because otherwise I'm going to save it and it's going to be messed up. When you look at the graph, the mass and the volume both change. Agreed?
Mm-hmm.
But is their ratio changing?
No.
Therefore, no matter how much I measure, don't I keep getting basically the same density?
Mm-hmm.
So think of that question again and what we just said, and what do you think?
So no matter how much substance you measure, density is still the same.
Right.
Did that make sense? Also, for the conversions tomorrow, you know when we did the density quiz, those were confusing. Can you make it like simpler, like that table on the other worksheet?
Let me think. So when you say, I'm trying to understand exactly what you mean. So you're saying like, can you be more specific? Because I'm not clear what you mean.
So basically on the density
The-
quiz that we had, it was like 1 over like 100 or 1 over 10 to the third, and like that confused me. But then when we had the other quiz
Well,
that we did on the worksheet that we did, like the conversions were like, I don't know, simpler.
well, we didn't have a density quiz. We had the worksheet, if that's what you mean. But I'm
Yeah,
not.
yeah, 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 yeah.
Yeah, you know what? I'll tell you. I'm not sure what's confusing. So you tell me, like when you're on the test, if you think I'm not sure what this
Oh,
means, just ask me,
okay.
and I'll
Thank you.
try to clarify. Yeah.
Thank you so much. Have a good night.
You too. No problem. Noon, did you have another question? All right, then I'm shutting her down.